Question 3. So this question is about fuel cells, and we've got electrode potentials here. So these are all half equations. They're all reductions. So if you consider that the reduction oil rig, or oxidation is loss, reduction is gain, so they're all gain in electrons. And the larger the value, the more likely it is to go ahead. So this one's very likely to go ahead to make F- ions. This one's unlikely to go ahead because it's the lowest value and it's minus. So something that's positive will go ahead, something that's less than 0, something that's negative won't go ahead. And when you combine two half equations, you have to reverse one round the other way because they can't both be reduction. You've got to have oxidation reduction, you've got to have redox. So one's got to be oxidation, one's got to be reduction. When you reverse the equation the other way, then you add these two numbers together. So if, say for example, that one and that one we're considering, and this one went ahead and this one went back the other way, you'd minus that number and then add the two together to give a positive value overall for it to go ahead, for it to be feasible. So we've got each of these reactions happening in two cells joined by a salt bridge. Explain the function of the salt bridge. It allows ions to move between the salt bridge and complete the circuit. So ions in the salt bridge can move to complete the circuit. So it's allowing ions to move, electrical charges to move, to create a circuit between the two cells. Use data to choose the halide ion that is the weakest reducing agent. So halide is something like F minus, Cl minus, Br minus, I minus. So if we have a look at these, we've got F minus, Cl minus, Br minus, and I minus. Even if you weren't sure, then you'd pick either that one, F minus, or I minus, the least one. So it's never going to be the two in the middle. It's never going to be Cl and Br. If it's the weakest reducing agent, it's at least one of those two. Now let's consider what weakest reducing agent is. So this one's really going to go ahead because it's got a large electrode potential. So F minus is really going to be made, plus 2.87. So F minus really likes being reduced. It likes being reduced, gaining electrons to become F minus. So it's unlikely to go the other way. It's not going to go the other way. Those halide ions are not going to be oxidized. So it wants to be reduced. It doesn't want to be oxidized. It doesn't want to lose electrons. So let's consider a reducing agent. Reducing agent reduces something else, causes something else to be reduced, and in the process it is oxidized. So your answer is F minus because it really doesn't want to be oxidized. It doesn't want to reduce something else and become oxidized itself. So it doesn't want to become oxidized. It wants to be reduced. It wants to move to the right hand side. So your answer is F minus. Justify why sulfate ions should not be capable of oxidizing bromide ions from the data. Justify why sulfate ions should not be capable of oxidizing bromide ions. So let's have a look at sulfate ions. Sulfate ions are these, SO42 minus. So we've got plus 0.7. So if that goes ahead, it's plus 0.17. Bromide ions are here, Br minus. So if we reverse that, that becomes minus 1.07. So plus 0.17 minus 1.07, if the bromide ions are going in the opposite direction, gives a negative value. So sulfate ions is plus 0.17. Electrode potential for bromide is minus 1.07. So the sulfate ion would be reversed. It would give a plus value of 0.9. So that's actually what's going to happen. The sulfate ions would go this way to give minus 0.17, and the bromide ions would give plus 1.07. So that's the way that it would go rather than the other way around. So sulfate ions should not be capable of producing of oxidizing bromide ions. That's true because the sulfate ion has a lower electrode potential than the bromide ion. So if either of them is going to be reversed, it's going to be the sulfate ion minus 0.17 to give an overall positive value of 0.9. So the electrode potential for sulfate ions is less than that of Br, and because it's less than that, this would be the one that would be oxidized and go to the left hand side to give a minus 0.17 plus 1.07, therefore gives a positive value positive EMF overall. Calculate the value of the EMF of the hydrogen-oxygen fuel cell operating under alkaline conditions. So you need something with hydrogen and oxygen in the two equations, and alkaline conditions, alkaline is OH minus. So you're looking for something with hydrogen and oxygen in, and alkali is OH minus. So the two equations to use are these. Now, which one's going to be reversed? It's got to give a positive value overall. So if that stays positive and this one gets reversed to give a positive 0.83, this one is going to be reversed. So 4OH minus plus H2 is going to give 4H2O and 4E minus. So plus 0.4 and this one reversed plus 0.83, 1.23 volts. There are two ways to use hydrogen as fuel for cars. One way is a fuel cell to power an electric motor. The other way is as a fuel in an internal combustion engine. So it's just the major advantage of a fuel cell. It doesn't waste as much heat energy.